part of the results of my PhD thesis, which I defended earlier last year. The thesis was carried out in the framework of Seido Lab, which is a joint laboratory between EDF and Telecom Paritech. I was here at Links, and also I was part of the AIT Digital doctoral training program. And I'm currently working at ICT4V, which is a technological center similar to Links in Uruguay for the region. I'm leading energy projects and coordinating the blockchain working group. And also I'm working as an innovation director in my own company, which I co-founded before starting the PhD. And I'm working also in energy and blockchain stuff there, trying to push that also. But today I'm going to present mostly things related to my PhD, but to the application side of, not the academic results, but the application. How did I use blockchain to create peer-to-peer energy markets? And then talk about a little bit about other use cases, not only peer-to-peer energy trading. So first, the context. For the context, we have a distribution grid, an electricity distribution grid with generation, transmission, and the wholesale market actors there. And what we have is the energy transition is pushing for a lot of distributed energy resources. So distributed generation, electric vehicles, storage, and particularly those resources are owned by different actors. For example, by a household owner owns those resources, owns the control of those resources. And therefore, those actors can become not only a consumer, but a prosumer, an actor that has an active role in the grid. But the thing is, in order for that to become a reality, there are very high costs. For example, if we want to create a sort of market, we would have to, for integrating these consumers, we would have to add a centralized actor, and then as it's a centralized actor, we have to add an auditor, and that makes the cost of transacting with those consumers quite high. So then we have also problems like provider lock-in, that the company that is going to manage these resources is the company that is usually company that is exploiting the resources, selling them, and you cannot sell it to another company, for example. So you are locked in, you are dependent on those companies. And then what that particular company, let's say the aggregator, does with the resources is not visible to the other actors. So there is a lack of visibility of what's happening on the grid, and that's an important problem. And another problem is the lack of coordination. I mean, what this, for example, an aggregator does with some flexibility here is not seen, and we cannot coordinate for what is used, if it's used for local needs or for overall global needs. And for all of these reasons, these kind of problems, blockchain could provide a solution, and we proposed a blockchain local markets in order to get that coordination, get that visibility, reduce costs, and avoid the provider lock-in. So I'm going to talk to you about more like the design and the implementation. I mean, how did we organize the architecture for using blockchain, and some learnings around that. So first we started in 2015, thinking about how to coordinate the resources that produce, consume, store energy inside the household, and we realized that there were plenty of controllers inside the household and plenty of opportunities of conflict among these controllers. I mean, if I wanted to reduce consumption, maybe a controller for quality of air would conflict and open a window, and then I would have a problem. So we proposed firstly using blockchain in that domain, but it was kind of too early, because we tried to put blockchain inside of one of these sort of Raspberry Pi devices, and it was impossible. So we moved forward and saying, okay, let's assume we have this control and we can avoid conflicts, and let's decide how, once we control the households individually, how we can coordinate all those households in a way that is positive, not only for them, but also for the distribution grid. So we proposed an architecture based on a local energy transactive platform that we implemented using blockchain. in order to coordinate which kind of services we could apply. And in particular, the services we focus, it was a local market, local energy market, that would allow households to sell their excess of energy to their neighbor in a way that was positive for the electricity grid. So how did we map this problem kind of to a blockchain scenario? So here we have the functional architecture, so the architecture inside the household, and the different actors that want to interact with the flexibility resources that households have. And we map this by assuming that each household would have a trading agent that would have a sort of like wallet, like a light client. And then that each one of the actors that would like to provide services on, or have visibility on what's going on the electricity grid would run a full node processing transactions and maintaining a blockchain over which we would have the applications, let's say, running on that blockchain. And in this case, the application is a renewable energy balancing market, which is represented here by a network of smart contracts. Each one of these is a network of smart contracts. It's a smart contract with a specific functionality. And one of the things that is important to mention is not, there should be much more smart contracts here that are playing all the functions that are needed because coding in blockchain is particularly different than coding in other languages. So this is kind of the mapping that we did. And regarding the technologies that we used like Tendermint for the distributed agreement part. We used Monax as let's say, the virtual machine that would allow us to implement smart contracts over the Tendermint distributed agreement, and we use Node.js for the wallet. Okay, and the idea was to use Cosmos to extend this to have different networks and integrate different blockchains in different neighborhoods. So that was the main idea. So some unique design features, because after this we did this very early. We did this like early 2015, and now there are plenty of other peer-to-peer energy markets being presented there. But I think this our approach for the design is still kind of quite unique, in particular because we do ex-ante trading. For example, we trade before the fact, and we ensure that we validate the transactions and allocate the trading, the rewards, once the transactions are being verified in the same time. So we are not only trading certificates, we are trading real energy and incentivizing households to trade with each other and balance to reduce cost on the grid, reduce peak power, etc. And also, as we do this, we realize that this has a positive impacts in plenty of things, but can have negative impacts. And most of other approaches, they don't talk about this. But for example, one of the most important examples is voltage imbalance factor. We have 3 phases distribution grids, and each house is connected to one of the phases. And when I balance one house that is producing in one phase with another that is consuming in a different phase, that creates several issues on the distribution grid. And we attack those issues by adding, for example, another functionality that explodes the visibility that the blockchain provides. So the operator can know what actor is going to inject how much, because they have a commitment. So with that information, they decide on which phase, which house should be connected to in a dynamic fashion every 10 minutes. And that can solve the problems related to voltage imbalance factor that are not solved for any other peer-to-peer energy market that I've seen. Other aspects are forecast uncertainty, because users, as it's an ex-ante mechanism, houses decide on the forecast, what they expect to be producing or what they expect to be consuming. And for that, we also had to add another mechanism that would use that visibility in order to ensure, with a game theory mechanism, that the grid would be balanced locally. And the operator wouldn't have problems regarding high currents or voltage deviations, etc. Other aspect is that plenty of peer-to-peer energy markets are based on a some cryptocurrency or some ICO that they made to sell tokens. And that leaves like one central actor with the power of decision and over a cryptocurrency and a variation of cryptocurrency that has a huge impact on the users. So we proposed a token that has different properties that is controlled by, let's say, by the utilities and with some clear rules and value pre-established, which is different to other market proposed. And then we also focused in a market design which has certain properties that simplify the implementation. For example, we propose a strategy proof mechanism that simplifies the billing strategies of the users. So the users have to propose, their optimal is to propose what their evaluation. So you don't have to think in crazy strategies, whatever. So it's much more simple. So this is more or less what we propose in our PhD, in my PhD. And I wanted to comment a couple of things regarding coding issues that we have in developing smart contracts. One of these is that we have really limited resources in terms of storage, memory, processing, etc. And also regarding features, we have limited libraries. So for example, I needed to do a sort, and I had to code the sort myself. So you cannot call a function that is sort. So you have to code kind of everything yourself. The fact that the code is immutable, every time that you need to update a smart contract, you are erasing, this older smart contract still there. So you have to create a new one and tell the users point to this new one. So instead of that, you have to create a set of smart contracts that would interface the client and never change. And then you would update the pointer to the new. So that makes that the coding is quite different. The other thing is that we used to listen that they are autonomous and trustless and so whatsoever. But the thing is that when you don't have a cron function, if you have like a market like ourselves, somebody has to open the market. Someone has to decide when the market would close, and you cannot like set a timer. So you need to trust somebody to open, close the market, etc. And the other aspect is that the maturity of the code is quite, it's not mature, so it takes a lot of time, lots of effort, and you have to change and adapt to bugs and so on. So I wanted to mention like a couple of things that most of the applications of the company that propose energy, applications of blockchain are based on peer-to-peer energy markets, and I wanted to mention that we have been working with the utilities on much of the applications regarding digitalized incentives, auctions, etc. And we work also in traceability of end-to-end traceability, and we won a prize on the Hyperledger Global Forum. And we also have, besides that, I wanted to mention that there are also already commercial solutions. Before some time ago, we didn't have commercial solutions. In particular, what we have is, for example, Power Ledger that does peer-to-peer energy trading, and also, for example, Slockit with the RWE, share and charge, that allows you to share your charge point, for example, and that's happening today in Germany, for example. So this is not only peer-to-peer energy trading, and it's not only proof of concept. We are already in the stage where designing business models and so on. Sorry for the extension.